Welcome back, everybody. Next up, we have Clay Smith, who has been our reliability lead through the duration of this study, and he's going to talk about the longevity study that has gone on within this study, asking the questions about reliability of the flight system, continual operation of the ground system, and organizational considerations beyond to encompass the longevity of the program as a whole. With that, Clay.
Thank you, Michael. Appreciate that. My name is Clay Smith. As Michael said, reliability engineer at the lab, and we'll be talking about the longevity study. Next slide, please. And so as Michael provided in the input, what we're really looking at are two principal goals here. One, understand the processes that will ensure success for the flight system, the ground system, and the organization of the staff and institutions. And then secondly, and to look at what history can tell us about the potential success for a spacecraft lasting 50 years. Next slide, please. So the topics I'll talk about are the reliability and lifetime, a lot of the history and baseline assessment, and then I'll show you what went into that and what that looks like. Talk a little bit about some of the recommendations and findings for the ground system longevity and the organizational considerations. Before I go into that, I do want to make sure that I thank and acknowledge a few people outside the lab. One, Dr. DeGinta Das from the University of Maryland, the Kelsey Center, provided a lot of good help and research for the physics of failure models that we'll be talking about later. And also Dr. Janet Vertesi from Princeton, who authored a lot of the organizational literature and findings that we have as well. And then before I go off of this, to thank Tony DeVinti and Nancy Lindsay. Both are NASA Reliability Tech Fellows, provided a lot of support and consultation in putting this study together. So thank you to all of them. Next slide, please. So the reliability, certainly as defined by NASA and defined elsewhere, is the probability that an item will perform its intended function for a specified interval of time under stated conditions. It basically says what's the probability that will last and do the mission correctly. And this translates in a design philosophy that I'm sure you saw a lot with the engineering discussions, that the spacecraft bus is mostly redundant, if not fully redundant. There are places that we can't achieve full redundancy because of mass and power, like flying two propulsion tanks and double walling the tanks themselves and things like that, right? So there's just some things that are accepted as single point failures, and there's a lot of engineering to go and shore those kinds of things up. The instruments are mapped to the science requirements such that the loss of any one instrument won't fail the mission. And with the discussion of the science traceability matrix, you saw a lot of that. We took that and mapped it with the same reliability methodology logic to ensure that that's not the case. One exception, and that's the magnetometer. And the magnetometer shows up as being needed for just about all of the science questions and objectives that are being considered. And so with that, then we've decided that the magnetometer will probably need to be redundant in and of itself. What the form of that takes, we're not sure, whether that's internal redundancy or you fly multiple of them. That's left for the development activity later. Next, where does the 50 years come from that we talk about? So the table here shows, roughly what those durations are for the different phases. And so all three of the phases that we talk about add up to this 50-year goal. And then, as Michael talked about earlier this morning, there is, extended mission that continues that 50 years out further and further. Next slide, please. So a couple things about what the historical record tells us. Well, one, that note you see on the side, as I was going through early literature on what Air Force and NASA were talking about in terms of, long duration missions. I came across this report from 1964 where they were talking about reliability of long-term missions, and they were defining long-term missions in terms of 3 months to 2 years. So just to give you a perspective that, yes, NASA continues to talk about this, but the perspective of what long-term means has certainly evolved as the technology and the industry has evolved. So things about spacecraft reliability. Spacecraft tend to last a very long time once they pass the initial deployments and commissioning phase. And this basically says that if the mission is designed correctly for the environment it's going to go into, they tend to last a very long time. The other thing that you start to see in the literature is this understanding, gradual understanding from reliability or about reliability behavior of spacecraft is that, bringing in jargon, that the models are Weibull instead of exponential, meaning that the failure rates are time dependent, not constant in time. And that time dependence is that the failure rate decreases over time, meaning that as spacecraft tend to last longer, or the probability of succeeding for the next several units of time becomes better and better. And so that rolls into how we model the baseline assessment of reliability, that we don't use the standard exponential decay function for that. Also in the literature, looks like part failures are not the primary cause. Certainly early on in the in flying spacecraft, that was the case, and it has gotten better over the decades. And when you start to look at the data, that the part failures is not the primary dominance. It really is things like failures that are caused by design errors or something like that. Changes in the environment, but not part failures. And like I said, the trend continues to get better on that. We also looked at physics models to explain failure mechanisms in the electronics. The failure mechanisms are well understood from an academic point of view and from the manufacturing point of view. So part of what we reached out to were part manufacturers to understand what they look at, what kind of testing regimes they have in place, and all of the potential failure modes and mechanisms that come into play for spacecraft, the manufacturers have a good handle on. What isn't really understood is extrapolating out beyond their data set. So the data set that they test for is 10 years, 15 years, depending on the parts. And extrapolating things out to 50 years is where the uncertainty comes in. But the understanding the failure modes of their technology is understood. So a couple of things about caution about looking at the historical data. So we can take a look at something like Voyagers that are 40 plus years and still running. What we're looking at here is 40-year-old technology. And so we need to be cautious about transferring a conclusion from 40-year technology to current technology, and whether that is going to exhibit that same 40 years plus behavior. Most indications are that it will, but the data isn't there explicitly to say that. Next slide, please. So as I mentioned before, success for spacecraft is very good. What you're seeing on the top right is a plot of interplanetary spacecraft mission success with the uncertainty around that. Mission success here is defined by the spacecraft lasting longer than its design life. And you see a couple failures along the way, but what you're seeing for the numbers here is the probability of success, about 94% with the uncertainty, 90% uncertainty, saying that it could be as low as, say, 86%. The chart at the bottom plots these same interplanetary spacecraft as the mission design life versus what the missions actually were. And here you can start to see what the data looks like in terms of how many things failed and how many things were just retired, turned off due to funding, ran out of fuel, things like that. The majority of what you're seeing here, spacecraft did not fail, even when they were beyond their design life. They were turned off, which starts to bode very well for looking at spacecraft that's going to last 50 years. And when we do the statistical analysis, I'll show you in coming up, that shows very well in terms of what we can actively predict. One other thing that's not shown here, we did the same kind of analysis for the RTGs. The RTG stated design life is 17 years. And when we start to look at the same kind of plot and analysis, we see that RTGs tend to last a lot longer than the 17 years. Next slide, please. So when we do the statistical analysis, excuse me, using the sensor data being ones where we don't have a failure at the end of life, right? A lot of these things were turned off. That will tend to bias the data a lot. So when we do the statistical analysis, the mean for interplanetary spacecraft is about 62 years. And wide distribution on that wide distribution is coming from the fact that we don't actually have a lot of failures to anchor this distribution. So the 90% confidence is 25 to over 100 years. But what it does start to say is that the indications for a long duration missions are feasible. And of course, these are missions that weren't designed to be lasting for decades, right? Even Voyagers were designed to last 4.5 years. So even without trying, what you're seeing is mean lifetime for that fleet, that population of interplanetary missions of 60 years. Next slide, please. So we take a lot of this information and information about the notional parts that the design team came up with for the architecture, And we have at the top level, the spacecraft has the bus that needs to work, and it's got the payload that needs to work. And there's models for the bus down to the subsystems and to parts, and same with the payloads, the models at least down to the payload level. And what you're seeing in the graphs here is our estimate for the mission reliability is 74%. The bus itself is 82% with a payload of 92%. Now, also take into account that those bars that you're seeing there are the 90% confidence limits around those estimates. So fairly large. And this uncertainty then needs to be reduced during a development cycle with more testing, with more data gathering on the specific parts that are going to be used, right? This is all work that needs to be done during the development process. Next slide, please. This is just an indication of how we decompose the science traceability matrix down to logic, i.e. a fault tree, and using the logic that was put together for that in order, how many of the questions needed to be answered for each objective and how many objectives needed to be answered. So all those various dots that show up on that matrix translated to a logic structure. When we did a Boolean reduction of the logic structure, we ended up with a couple of single point failures, the magnetometer, which I talked about earlier. And then the doubles that you're seeing here are what combinations of failures in different phases, being the phase one, the interplanetary phase, and then phase two being the heliosheath phase, etc. And what you're seeing here are the multiple combinations that the logic reduces to. And so all of these things are then put into the model as part of the reliability estimate for the mission. Next, please. What you're seeing here then is a framework for what a reliability program needs to look like. In the upper part of this are typical reliability analysis that need to be accomplished: failure modes and effects analysis, fault trees, probabilistic risk assessments. All those things are currently done on missions. And what we need to do in order to drive down the uncertainties for things lasting out to 50 years is to have an understanding of the physics of failure for these things, and then a testing program to support those models. And then therefore, the results of those support the probabilistic risk assessments to give us a probability of success. Next slide, please. Probability of failure models. Like I said, we did reach out to the academia and the literature there. We reached out to a number of the electronics manufacturers. The physics models have been identified and created over the last several decades. So that part is in place. More testing needs to be put in place to anchor what happens, outside the data set that's currently available. Next, please. A couple words about the ground segment. So the ground segment is a little bit different in that it is maintainable and repairable. So we don't have to worry about the quote reliability of them, although it certainly matters to logistics and cost in the out years. But there are other things that have to be taken into consideration, and that is, how do you put a ground segment together that bridges across multiple organizations, potentially multiple nations, and multiple generations of of engineers and scientists and stakeholders as the years go forward. And to that end, having a understanding of how knowledge is to be retained and made into information, how the stakeholder organizations need to endure essentially the funding process and support the commitments over decades. Right? These are things that take a little bit more consideration in a mission like this than a typical mission. Next, please. So a couple things that this breaks down to: software considerations, compliance with current space data standards, considerations for the hardware itself, understanding the obsolescence and the refresh and upgrade cadence through decades, and then of course funding that and making sure that people are trained up on things as they iterate through, a communications infrastructure and downlink that's likely going to change over decades, and how do things stay backward compatible to a spacecraft that was built now versus when these changes happen decades from now. And then, for data collection and archiving, relying on the planetary data system. So a couple considerations there. Next slide, please. The organizational issues and considerations. Right, this needs to be founded on strong technical and human components. Both of these are working hand in hand, and making sure that organizational human aspect endures through decades is one of the big considerations to think of. And just a couple of things that I'll mention. Succession planning needs to be built into the organizational structure and part of how the mission operates going forward. Part of that is mentorship opportunities, reaching out to new scientists, new engineers as they're coming in, making sure that that process of rolling people through to leadership positions eventually continues on a regular basis and not done ad hoc. It's actually planned into the process. Next slide, please. So just to summarize, then the reliability from the history and the preliminary estimates look like this is feasible, that meeting a reliability goal out to 50 years is certainly supported by the current data set. We need to reduce the uncertainties, and putting in place these physics of failure models to understand how things fail at end of life, out past 50 years, is essential. The ground system needs to pay particular focus on a couple areas: how we're going to evolve the hardware on the ground and the software, the infrastructure, and certainly the archiving of data for decades. And then the organization needs to certainly plan for succession as part of the organizational structure. And with that, I'll open it up to questions.
Thank you, Clay. We have one question in the open set. John Cooper says the designated archive for a primarily heliophysics mission would be NASA Space Physics Facility, and only secondarily for planetary science, the planetary data system. John, thanks for pointing that out. We do hope that we're going to be dropping data into both. Clay, we're a little bit over, and I don't see any other questions at the moment. So I'm going to say thank you very much, and thank you and the team working on this for the very rigorous, disciplined approach to asking this question of 50 years. We're not going to get there with hand waving, and the path that you've started us on here is the way we need to go. Thank you very much.
Yep.